Have you ever noticed how a thermostat precisely regulates room temperature, or how an automatic cruise control maintains a steady speed? These systems do not just reach their target, they settle there smoothly and quickly. For second-order systems, the settling time, which is the time it takes for the system output to reach and stay within a certain percentage of its final value, is primarily determined by its damping ratio and natural frequency. Specifically, these formulas give us a direct way to calculate how long it takes to settle to within either 2% or 5% of the final value. The core mechanism lies in the system's characteristic equation, which defines its dynamic behavior. A second-order system can be underdamped, critically damped, or overdamped. The natural frequency represents how fast the system would oscillate without any damping. The damping ratio, denoted by the Greek letter zeta, describes how oscillations decay. A higher damping ratio means less oscillation and faster decay, leading to a quicker settling time for underdamped systems. For overdamped and critically damped systems, the response is generally slower and without oscillation, making the settling time longer than ideal underdamped cases. To calculate settling time, engineers use specific formulas derived from these parameters. For the common to percent settling time criterion, the formula is approximately divided by the product of the damping ratio and the natural frequency. For the 5% settling time, it is approximately 3 divided by the product of the damping ratio and the natural frequency. By determining these fundamental parameters from the system's transfer function, you can directly plug them into these equations to predict the settling behavior. This mathematical elegance comes from the system's poles, which are the roots of the characteristic equation. For underdamped systems, these poles are complex conjugates, and their real part dictates the rate of exponential decay, forming an envelope around the oscillating response. The settling time formula essentially quantifies how quickly this exponential envelope shrinks to encompass the desired final value range. Understanding the pole locations is key to advanced system design and optimization. By understanding how damping ratio and natural frequency directly influence settling time through these precise formulas, engineers gain crucial predictive power. This allows for the precise design and tuning of control systems to ensure they not only reach their desired state accurately but also do so within specified performance requirements, minimizing unwanted oscillations and achieving optimal dynamic response for reliable operation.